All right, so today let's dive into something called toxicodynamics. It sounds complicated, I know, but it's really about a fascinating battle. What happens deep down on a molecular level when a foreign chemical gets inside our bodies? Something scientists call a xenobiotic.
So here's the big question we're tackling. How is it possible that just one foreign substance can set off something as serious as cancer? It seems kind of crazy, right? Well, that journey from a single exposure to a diagnosis, it's a really complex story, and we're going to unravel it together.
Okay, so what is toxicodynamics really? Well, think of it as the science of the crime scene. It's all about studying that exact moment a substance hits our body's machinery, things like our DNA or our enzymes. It's about figuring out the chain reaction that leads to damage, and it really zeroes in on how the amount of a chemical, the dose, relates to how our body reacts. So picture this. A foreign substance gets into your body. The second it's in, it hits a critical fork in the road. And the path it takes, well, that's everything. It determines if it just passes through harmlessly or if it kicks off a seriously damaging chain of events. And this is where our body plays two kind of contradictory roles. On one hand, our metabolism is absolutely brilliant. It's a detoxification master, breaking stuff down so we can get rid of it safely. But, and this is a huge but, sometimes that exact same process can totally backfire. It can accidentally create something even more dangerous, a super reactive substance called a metabolite. And this is exactly where things can go horribly wrong. In the process of trying to protect us, our body can accidentally activate a substance, basically turning it into a tiny molecular weapon. These reactive metabolites, are super aggressive. They go hunting for our DNA, and when they find it, they lock on with these incredibly strong bonds. Think of them like permanent chemical handcuffs. And just like that, our genetic code is damaged. So, that damage to our DNA? Well, that brings us right to the main event for this explainer. We're going to take a closer look, step by step, at how chemical exposure can actually lead to cancer over time.
Okay, this flowchart here is going to be our roadmap. I know it looks a little complicated at first glance, but it really shows the whole story, from that first exposure all the way to disease. You can see the safe paths, detoxification and repair, but you can also see that dangerous path, the one that goes through that metabolic activation we just talked about, leading to initiation, promotion, and finally a tumor. And it all kicks off right at the top when something called a procancerogen, basically a substance with the potential to cause cancer, gets into our system. So the very first absolutely critical step on this dangerous journey is called initiation. This is it. This is the moment that first genetic mistake happens, the one that shoves a perfectly normal cell onto a brand new and very dangerous path. And what's so important to get here is that this isn't some slow, gradual thing. No, this initial damage happens fast. It's a rapid-fire event. And once that change is burned into the cell's genetic code, it's permanent. It is irreversible. For that one cell, there is no going back. And this visual makes it super clear. Over on the left, you see normal, healthy DNA, that classic double helix. But then look at the right. That's the same DNA after it's been hit by one of those reactive chemicals. That change, that modification right there, that is the core event of initiation.
Now, our bodies aren't just going to take this line down, right? We have these amazing DNA repair crews constantly on patrol looking for exactly this kind of damage. But they're not perfect. They're not foolproof. And if a mutation doesn't get fixed or gets fixed wrong before that cell divides, well, that mistake gets locked in. It's then passed down to every single one of its daughter cells.
So you might be thinking, okay, one mutated cell, how does that become a full-blown tumor? Well, after that initial hit, initiation, we move into the promotion phase. This is where that one damaged cell is basically encouraged to multiply over and over, creating a whole army of clones. After that comes progression, where these cloned cells start changing even more, becoming more aggressive, and eventually forming a malignant tumor. And the key thing is, this whole process can take a very, very long time. We're talking years, sometimes even decades. Okay, but cancer, as terrible as it is, isn't the only way these things can hurt us. It's just one possible outcome. These foreign substances can actually damage our bodies in a whole bunch of different ways. So let's just quickly run through a few of these other pathways. A substance can be mutagenic, which means it causes mutations directly. It could be neurotoxic, meaning it specifically attacks our brain and nervous system. Or it can mess with development and reproduction,
which can affect things like fertility or an unborn child.
You know, when we talk about those mutagenic effects, there's a really critical difference we need to understand. There are two types. First, you've got somatic mutations. These happen in your regular body cells. They're not passed on to your kids, but they can cause big problems for you, like cancer. But then there are germinal mutations. These cause damage to the DNA in sperm or egg cells. And these are the ones that can be passed down, tragically, to future generations.
To make this whole neurotoxicity thing a little more real, let's use an example we've all heard of: lead. We all know lead is bad for the brain, right? But do you know why? Well, it all comes down to a simple case of mistaken identity on a tiny molecular scale. Okay, so here's how it works. Your brain's nerve cells need calcium to talk to each other. They use it to send signals across these little gaps called synapses. Now here's the problem. To your body, lead looks a whole lot like calcium. So lead can sneak in, impersonate the calcium, and block the real stuff from doing its job. It totally disrupts that critical communication process. It messes with the fundamental chemistry of how your brain works.
So after hearing all of these mechanisms, you'd think it would be pretty easy to just point to a chemical and say, yep, that one's dangerous. But, you know, in the real world, proving that one specific substance caused one specific disease in people is, well, it's incredibly difficult.
And here are a few big reasons why. First off, there's the time lag. We're often talking about decades between when someone is exposed to something and when a disease like cancer finally shows up. Second, we're almost never exposed to just one chemical at a time, right? We live in this chemical soup of co-exposures. And last but not least, just imagine trying to figure out exactly what someone was exposed to and how much 20 or 30 years ago. It's a huge, huge challenge for scientists. And this all leads to a really, really important point I want you to take away from this. Just because a study comes out and says it didn't find a link between a chemical and a disease, that does not automatically mean the chemical is safe. All it means is that in that one particular study, they couldn't find a connection. It's like that old saying, the absence of evidence isn't the evidence of absence. So we kind of end up back where we started, but now, hopefully, with a much deeper understanding. We've seen this incredibly complex and sometimes faulty battle that's happening inside our own cells. Look, understanding these toxic pathways doesn't give us all the answers, not by a long shot. But what it does do is give us the tools to ask better questions, to think a little more critically about the complicated chemical world that we're all living in every single day.